on S bar, we would like to get the pullback of that. And it's denoted by the same expression, which would be a alpha, the pullback of alpha. And that's now a bilinear form on S. So that's defined by, well, like it's like a similar story as before. What we can do, what we have to do is essentially we have to define that value where P is an arbitrary element on S, point on S, and we have two tangent vectors that live on S, and we have to produce a number. And the only information that we have is that there's an alpha living, but like it's living on S bar, and our tangent vectors are living on S. So the only natural guess what you could do would be, okay, we transform both of these tangent vectors so that both gives us like tangent vectors which are now living on the target. Both of them. So if you have now two tangent vectors on the target, then we can plug them into alpha at the correct point. And that gives us, again, a number. And you can see, again, because TPF is linear and alpha is linear, you see that F star of alpha will be also linear. So it gives us, again, a bilinear form. And it has the same symmetry properties. If alpha was symmetric, so if I can change these ones and I get the same point, then also the pullback of alpha will have the same symmetries. Or if I get like a minus sign here, then also the alpha star will be antisymmetric. And so there is again family of maybe bilinear forms but this time on S with the same symmetries as alpha. So if I, like symmetries means like what happens if I exchange two tangent vectors. And we have already seen a construction like that. Namely, in the chart representation. So if psi is a chart on S, and now we can consider U and S as just like the surfaces. So what it means is we can pull back information from S to get them in U. Then the pullback, say for example, of the second fundamental form is just the chart representation of that fundamental form as we have defined them like previously. So that if you look at the formula how we defined this second fundamental form, that was exactly using the same kind of trick here, where we used the chart to push forward the tangent vectors, and then we got and plug them into the second fundamental form on S. So that's an example. In the same way, we also can pull back if alpha is the 1 or 2 form. So the chart representation would be one example where we have already seen these kind of objects. Okay. And now we need like two important properties. Namely that this pullback operation of 1 forms and 2 forms is like nicely compatible with the wedge product and nicely compatible with taking the exterior differential. So if alpha and beta are 1 forms on S bar, then what we would like to calculate is the pullback of the wedge product. And we would like to calculate what is the pullback of d alpha. So maybe I just do that, and then we write on the right-hand side what comes out once we're finished with the calculation. Maybe I leave that over there. And okay. So proof. So let's see what happens when we calculate that. So what we need is we have alpha and beta are 1 forms. We take the wedge product. That gives us a 2 form. And then we use the definition over there to pull back the 2 form on S bar to a 2 form in S. And we would like to find a formula for this. So what we have to do is we specify in point P and two tangent vectors at that point. And now we have to calculate what we get and see what happens. Well, the first thing would be we use the definition of the pullback to just like define and say what it means. So we have alpha wedge beta. We need to evaluate it on f of p using, so this is just like this equation here, but for alpha we just now plug in the wedge product. So that means we have to transport both of these tangent vectors with the map. So that's the definition of the pullback. It's just a push forward of the tangent vectors. Well, now I don't have much choice. If I want to calculate that, I need the definition of the wedge product. So let's use that. So it's alpha at f of p, evaluated on the first times beta f of p, evaluated on the second vector, minus, and then alpha evaluated on the second, and times beta evaluated on the first tangent vector. Okay, so now we look at these expressions that we get here, and what you see is that this expression over here, this one, is exactly what we wrote up here. that's the same expression, that if you have alpha 1 form and you push forward like a vector in there, then what it is like exactly the pullback. So we can write it as the pullback of alpha evaluated at the point P in the direction of F. And then the same things happen here and happen here and here. So we get times the pullback of beta at the point P in the tangent vector W, and here we get the pullback of alpha in W times the pullback in beta in the vector V. But that's nothing else than, again, a wedge product evaluated on two vectors. Namely, it's the wedge product of the one form alpha on S times the wedge product of the one form beta, also on S, and then evaluated on these two vectors. So what we've shown now is that the pullback of the wedge product, because the vectors were arbitrary and the point were arbitrary, means that the pullback of the wedge product is equal to first doing the pullbacks and then taking the wedge product of the resulting one forms. So that's the first. And hence you might be able to guess what we would like to have here, namely also that F star is the same thing as taking D of the one form and then pulling it back. So the second equation is like a little bit more complicated to establish. For the second point, it's kind of handy to work in a chart. So let a chart on S bar actually centered at F of P. And what we would like to calculate is at the point we have the chart, and it's actually a chart on S, sorry, centered at P. So what we would like to do is now calculate this two form, which is a two form on S. So it's this guy here is a two form on S. And we use a chart on S to calculate that. So we use the tangent vectors that you get by taking the chart, and then you have like a push forward of phi x. So these ones here are nothing else than what we denoted as t phi y and t phi x, essentially. So these are the push forward of the canonical coordinate vectors. And then we plug these ones in the 2 form, that comes from D. And now we can use the definition of D, which was that if you calculate it in this kind of like coordinate, what happens is that we take the 1 form that we want to evaluate it, and we plug in at the point phi, and so what this is like, what this means is we have d phi, which is like tangent vectors here on U. We get an induced vector on S. We plug that vector into the pullback of alpha. And then we get a function that depends on x and y, and we take the derivative on x. And now we have to do the same thing, but with like minus sign and x and y walls convert the opposite. So that's here. It's nothing else than the definition of the operator D, which was defined like if you take a chart like this, and then you have these 2 vectors you plug in, then you can calculate the D of that using this formula. Okay, so now we don't have much choice. We have to use the expression here. We have to use the definition of the pullback. So what this means is we take alpha at f of psi of xy, and then what we have to apply here is that it's t of psi of x of f applied to tx of y psi in the dy direction. Now we have to close all the brackets. So that's the this term here. And now we look at this example here, which if you chase a little bit like the definitions, then you will see that this one is actually t of x and y of the composition of f of phi in dy direction. So that means here we first have y, which is living on u. We push it forward to get a tangent vector on s, and then we push it forward with f to get a tangent vector on f bar. And just by looking at like curves, you see that this one is the same thing as like taking again a vector on u, but now just directly pushing it forward by this map, which goes from u to s, and then from f to s bar. So that's like a chain rule and like a relatively simple exercise to verify that these ones are the same. And of course, you can do a similar trick here as well, where we can write this one as t of alpha of f psi of x and y, evaluated on tx y f of phi, and now in the dx direction. And now you look at like this formula again, and you see that it's actually we would like to compare it anyway to d alpha. And the nice part is that we now see here something that looks like d. Namely, it's the same kind of expression of a dx, and then we plug in the one form in like the dy, y in a one form, and then we have like minus dy, and we plug it in the x form. So that's just looking at this equation. You see that it's again the exterior derivative So what you see is that it's d of alpha, and now we just collect like nicely which points, namely it's evaluated at a point f of phi of x and y, and written as tx y at a point f in the x direction, and in the y direction. And now we can essentially reverse that operation that we had, namely we can write this one again as tx of phi of x of y of f evaluated at t of phi at the point x and y in the x direction. And similar here. And then you see that it's actually now the pullback by f of d alpha. So what we get here is that it's the pullback of f of d alpha, and then evaluated at a point phi of x and y, tx y, dx, tx y, phi, dy. What is now the upshot is that if you compare these equations, you see that we have like tx of phi and dx and dy, both of them are like on the same side. So that means, because they span the tangent vectors, that means we can read off that d of f pullback of alpha equals what we have here, namely f star of d alpha. And that was exactly this equation that we had over here. So that's finished the proof, and this one is a bit more ugly with like the notation, but I think it's like a kind of like a nice formula that is very handy most of the times, because sometimes it's easier to calculate d alpha directly and then doing the pull back, and sometimes it's easier to do the other side first, where you have like always. I mean, it would also be a valid equation, but that one makes more sense. Yeah, it's correct, yes. So, like sometimes it's easier to first calculate d alpha and then take the pullback, and sometimes it's easier to first do the pullback and then take the d. And that's it's very handy to know that it's kind of like, yeah, it doesn't matter. So, like here, it's like really taking d on S bar, and here it's the d on S. So that's sometimes nice if you have, for example, some complicated surface, like if the coordinates look very ugly on S bar, and you have to pull back it to S, then it's usually easier to first pull it back and then do the calculation on S. If S is a nicer surface, for example, you have nicer coordinates. Good. I think that's enough for now. So let's go in a break, and then afterwards we discuss some applications of this push forward and pull back to like transformations, where like you have the map, which is like taking that surface to that surface, and we would like to study how objects are related on these two surfaces. So let's continue in 15 minutes, 5:30. and usually not in general.
But we have actually have the push forward of the function and the pull back of the function. We use the push forward of a function to define the pull back of the tangent vector and use the pull back of the tangent vector to define the push forward of the tangent vector to define the pull back of the.
How do you push forward a function? How do you push forward a function?
Push forward a function. Oh, yes.
So usually that's the problem, that you can't push forward the function, and that means also you can only push forward tangent vectors, you can't pull back tangent vectors. The only alternative would be if your f has actually an inverse. So if that's f is bijective, then you have an opposite map, which is then a map from S bar to S. And then you can now use the push forward or the pull back of that map, which is now reversing the arrows.
That's why.
Yes. So that's this equation here is just like this equation, where you have the push forward of two.
This equation we haven't proved it.
No, but it also holds. Essentially, you just write down the definition.
Push forward, so it's actually something I don't know how to describe. The inverse of these two functions, something to do with minus one. The inverse.
So the important part here is that it's this one is general for arbitrary functions f and g. That makes completely sense. The important property is that if you have an inverse, then you can actually now say you can push forward vectors from S bar to S, which you usually can't. So that gives you an opposite direction, but that really needs the inverse. And
I mean, the inverse of these two functions. The inverse of the sequence of the two functions have something to do with this kind of operation. Because this is push forward and this is pull back. So we change the sequence.
yes, but there's no direct way pull back to f minus 1. It's just that the arrows are the same. Yes.
And G, so we G first and F next.
Yes. Yes. Do you have a question?
I have to generally for this differential derivation, so I want to teacher to have a quick review.
Yes. So that was these two equations, two features. Yes, the ones, the parts that you missed. If you can read it.
I don't understand. It's a function of x, y.
Yes. Yeah, so that's what is meant here is that really you have to think of this guy here which is a function, right? It's this one is a tangent vector in U, this one is a tangent vector in S. So that means we plug it into a one form. So that gives us a number for every x and y. And then we take the derivative in x direction of that number. Yes. so that was a bit symbolic. Yeah, that was the definition of the exterior differential there. It means pullback. So that's the, it's a way to, so if you have F as a map from S to S bar, and you have alpha, which is a one form here, then there's a way to get back a one form on S. And the way it is defined is that we have alpha, the pullback, it's written as like the pullback of alpha. We have to give a point and a vector on S. And what we do is we have alpha, fp, and then we take the tangent map. So that's the definition of that. So it's not really like dual, but it's like the what is called the pullback.
I can understand this. I only want to know if this notation has another meaning. But you tell me there's no.
I mean, it's like sometimes this guy here is denoted by F lower star.
Oh.
And the way is then that you have like T on S is just the same as T of F. That gives you tangent map vectors from S to tangent vectors on S star. And now what you have is one forms on S bar, and you get like one forms on S by the pullback. And that's usually, sometimes it's called like you have like some general object like which is called functors in category theory. It's like once you have an object that goes in this direction, then you have a dual object which goes in the opposite direction. And that's what is happening here, and that's where this notation is coming from the star. is that it's like the dual object to that, like the dual operation. But yes.
One point is the vector stereo. So F star on this F star one view.
Yes. So that would be like F star. You can see that as like the dual of that map. Yes. So the adjoint of. Yes.
So about shape operator, I can understand that it should depend on E3, so it's extrinsic.
Yes.
But in some way, it's mapping from the like tangent surface to another tangent surface. This can be revisited as a two-dimensional matrix.
Yes.
I just don't understand why two-dimensional matrix can be depend on E1, E2, and E3 because it's
like the map in itself, you're right, it's like just so that the shape operator in itself is just TPS and TPS, right? So in that sense, you need to only evaluate it on E1 and E2 in order to know what it does.
yes.
So like the map in itself, you could say like you can like make sense of in 1 E2, but it's almost like by definition a T minus of the E3. So you can't say like what this map is without knowing E3. Of course, you can like say what this guy here is by just saying it's the span of E1 and E2. But in order to say what that map does to E1 and E2, you need to know E3.
Okay.
So in that sense, it's extrinsic.
Okay.
I think it's no need to say it's a unit vector. If it's a unit vector means this term will be photo one. I think this term is used to normalize.
Okay, that makes sense, yes. I think that. Yep. Yeah, that's true. Yes.
You SS.
Oh, yes. Yes. Okay, there was really a lot of problems in that. Like this equation here is also, no, now it's already corrected. Yeah, you're right. Thanks. I will also change that. Thanks. Okay, let's continue. So the idea now is that we have like a general recipe to push forward vectors and curves and pull back one forms and two forms and also bilinear forms. One remark is that you can't do the opposite. You can't like pull back curves. Yeah. You can't pull back curves. You can only push forward curves. So there's no way to pull back curves or like to pull back vectors. It's really like just like a push forward of curves and a push forward of curves that is well defined. So there's no other direction except if you have if your map that you're like looking at is invertible and you have like something to reverse the arrows. But there's really like no way to, for example, like if you have a curve in S bar, like if you have a curve that, so you have a curve which is an S bar, and you have some map, then that curve might not be induced by a curve that comes from S. So there's usually it's usually not like possible to find a curve here such that you can push forward it to get the curve that you started with. So it's really like only possible if you have like a, for example, the inverse operation here, then you could push forward the maps. So that's so important that like really like only the, like in general, these notions that are defined make sense, the other don't. And now we look at like, come back to the original question. This was like related to banding. So we have like a sheet of paper, and that map is like saying we can like as our original surface, and then we apply some banding operation to it to get like a different surface, and that's the capital F. And like here I've drawn two vectors on the sheet of paper, and if you take like the inner product of them, then you get like a certain number, and then you bend it, and you see like the inner product will not change if you just bend it. Like for example, perpendicular vectors in the plane stay perpendicular if you bend them. So that's like different to say, for example, you have here two vectors, namely the one which is going like one vector, sorry, which is like going just like along the red line, which is like going like downwards, and then you have a second vector which is orthogonal, which you can just like think of them as like here this line in the horizontal direction. So and now I have an operation which moves this surface to like this kind of stretched surface. And what you see is like these lines which were originally perpendicular are no longer perpendicular. So like that means like things that like if you bend things, vectors which are like perpendicular stay perpendicular, but if you have like objects where you stretch them, then you can change like the lines which are perpendicular don't have to stay perpendicular anymore. So that's like a change, namely that like things like some operations leave the inner product invariant, and some other operations change that. So like and we would like to only study these kind of maps that like are behaving nicely with respect to the inner product, and they are what's called an isometry. So definition. Isometry of surfaces S and S bar is a map of the projective map from S to S bar. That preserves the inner product of tangent space, of tangent vectors. So what does this mean is that if you have two tangent vectors v and w on some point in S, then we can take the push forward of these tangent vectors to get two tangent vectors again but this time in S bar. And then we can take the inner product of these tangent vectors, and we would like to get that as the same thing as taking the inner product of the original vectors for all. And this one is equivalent to using the definition that we now just discussed, is that if you have the pullback operation applied to the first fundamental form, which gives you the inner product of two vectors, so that's the right-hand side, is the pullback of the inner product by f equals to the inner product to the fundamental form on I. So this one is the first fundamental form of S bar. So this one gets a bar, and this one is of course, the first fundamental form of S. So that's like why we now discussed like these operations of pullback, is that things like this inner product can be easily rewritten now in terms of like the first fundamental form. So that means like you have the first fundamental form on your surface S bar, you transport it back via f, and you compare it to the original first fundamental form, and they are the same. So that's what is called an isometry of surfaces. And generally speaking, you can think of that as like bending of some sheet of paper without any stretching. Like as I showed with the short here, if you stretch it, then usually the inner product changes. But if you bend it, then the inner product stays the same. Sometimes, for example, it's like happens that this requirement that your map is bijective is a little bit too strong. For example, you can imagine like the sheet of paper. If I bend it slightly, it's nice and like an isometry. But if I now glue them together, then from the geometry I didn't change much. The vectors are still perpendicular. But now I have like 2 points on the sheet of paper which correspond to the same point on the cylinder, because I glued that together. So like it's not really bijective map. So it's like, and that's what we need for that is like a refined notion, which is like called locally like a local isometry. Surfaces such that the point S as some neighborhood U S such that the restricted map of F restricted to U, which is the map from U onto F of U in S bar, is an isometry. So the example here is unrolling the cylinder, the local isometry, but not global one. Exactly, because of these point properties. to show you some more examples. So who thinks that so we have seen that the cylinder is locally isometric to the plane. Do you know some other objects which are locally isometric to the plane, which you can obtain by the plane just like by bending without like having some stretching going on? Yes, I heard it somewhere already. So like the cone would be, for example, one surface which is like isometric to the plane. Like here we have the cone, and like you can see like if you have like some object, like say for example this disk, and you can print this test and like just take it and like without any bending, with only bending without any stretching and like changing measurements of the vectors, you can plug that on the cone, and of course you can just move it somewhere in the plane. So these are like isometric operations, or like the surface, like the cone is isometric to locally to the plane. There's a little bit of like usually you can think of like an isometry really something as like that happens from bending, like in a continuous way. But there are certain surfaces which are isometric, which are not like obtained by just like continuously bending a given surface. For example, here we have an example. In the construction, it goes as follows. You start with this kind of like half torus, which you lay in like lay it like in some plane, and you just like eat half of the donut, and then you just lay it there. And then what you do is like you have like this curve where it touches the ground, and there you cut it open. And then the outer part, this kind of like part outside here, you just project just like horizontally on the plane where it's laid. So like previously this part went like up, and now we just project the outer part going down. And you can see with a little bit of convincing is that like this surface that you get is isometric to the surface that you started with. So you don't change like angles and stuff of vectors. But if you try to continuously deform this surface into this surface, you will see that like at some point, like there will be like a sheet of paper will like break or like crumble if you try to do that. Like what you would like to do is like what is happening is like on a cylinder or half cylinder, it would be starting like this, and then what you do is like you take half of the cylinder and like you slowly bend it downwards to get like this kind of shape. So with the cylinder you can do that, but now try to imagine like I can't do that because the plane is like if you have like the torus, you start with like this, and then at some point the paper doesn't go